Today we're going to discuss the basics of semiconductors and their role in the field of electronics. Before semiconductor devices even existed, vacuum tubes were the only devices available for signal amplification, switching, and other applications. Though vacuum tubes are functional, they're bulky, require high operating voltage, and are completely inefficient. When semiconductor devices like transistors were invented, semiconductors started to acquire a dominating role in electronics. Now, semiconductors are materials that are in between conductors and insulators when it comes to the ability to conduct electrical current, which explains the name semiconductors. The most commonly used semiconductor material in the electronics industry is silicon. After that, it's a compound known as gallium arsenide. Semiconductor materials have two current carriers, free electrons and holes. In an intrinsic semiconductor material, free electrons are produced when the material receives sufficient thermal energy that provides valence electrons from the valence band enough energy to jump to the conduction band and to turn into free electrons. When valence electrons jump to the conduction band, they leave vacancies in the valence band, and these vacancies are called holes. The number of holes in the valence band is just equal to the number of free electrons in the conduction band in this undoped intrinsic material. A semiconductor material becomes a useful electronic component by controlling its conductivity. However, semiconductor materials in their intrinsic state do not conduct current well. This is because of the limited number of free electrons and holes in it. But through a process known as doping, the conductivity of a semiconductor can be increased. Doping increases the number of current carriers by adding impurities with either more free electrons or free holes to the intrinsic semiconductor material. The number of free electrons in an intrinsic semiconductor material is increased in the doping process by adding pentavalent impurity atoms, or atoms with 5 valence electrons such as arsenic, phosphorus, bismuth, or antimony. To visualize this, let's examine an antimony atom covalently bonded with 4 adjacent silicon atoms. As we can see, only 4 valence electrons of the antimony atom are used to form covalent bonds with the silicon atoms, leaving an extra electron that becomes a free electron. So by adding pentavalent impurity atoms to an intrinsic semiconductor material, the number of free electrons can be increased, as well as the conductivity of the semiconductor material. Semiconductors doped with pentavalent atoms are N-type semiconductors, since the majority of its current carriers are electrons. In order for an intrinsic semiconductor material to have more holes, they are doped with trivalent impurity atoms. These are atoms with 3 valence electrons in their valence shell, like boron, indium, and gallium. To understand how trivalent impurity atoms increase the number of holes in an intrinsic semiconductor material, let's see a boron atom form covalent bonds with 4 adjacent silicon atoms. In this case, when the boron covalently bonds with the 4 silicon atoms, a hole is produced. This is because each of the 4 silicon atoms requires 1 electron from the boron atom, but it only has 3 valence electrons. In this case, we can say that by adding more trivalent impurity atoms to an intrinsic semiconductor material, it increases the number of holes and improves the conductivity of the semiconductor material. Semiconductors doped with trivalent atoms are p-type semiconductors, since the majority of its current carriers are holes. The doping process converts an intrinsic semiconductor material into extrinsic and produces either an N-type or a p-type semiconductor material. Combining the N-type and p-type semiconductor materials creates a boundary known as p-n junction. This p-n junction is the basis for different semiconductor devices widely used today, like diodes, transistors, and thyristors. So in this video, we talked about the basics of semiconductors, the intrinsic semiconductor and its poor conductivity, how doping increases the number of current carriers in a semiconductor material and improves its conductivity. We also briefly mentioned how different semiconductor devices were created based on the p-n junction.